All right, class, let's continue with solving logarithmic equations. So we're going to start simple again, and this is a very basic logarithmic equation. So we need to get into x. Of course, as we did with exponential equations, we have two options. Either you could simply change this logarithmic format into an exponential one. So again, remember, you keep the base the same. So 2 to the power of 4 is equal to x. Boom, you got x by itself. That, of course, is a 16. And we're happy. This is the answer. Or, how else do you get rid of a log? You put an exponential expression with a base the same as the base of the log on it, right? So to undo it, yes. So 2 to the power of log with base 2, they cancel each other out. So again, that simply means that x is 2 to the 4th. That's it. So there you go, there's your answer. So again, whatever you prefer, if you're good with switching to exponential to logarithmic form and backwards, there it is. 3 to the power of 2 is equal to x minus 1. So of course there's one extra step to get to x. So add 1 over, so x is going to equal to 10. But then again, what made the log really go away? A base of 3 under it. Yes, so either way you look at it, you don't have to do both, but I'm just showing you either one works just fine. And there it is. Okay, so let's up our game a little bit. There's a few more things going on around the log. So first things first, I want to get the log by itself, right? It looks better that way. So what can I remove in my way from the log? Of course, do not subtract 10 minus 4 because 4 is tied up into this multiplication, yes? So again, order of operations is multiplications before subtraction, so I couldn't subtract unless I multiplied the 4 to the log. But I'm definitely able to remove this 10. Okay, and now again, this log is multiplied to a 4. Of course, we can undo that multiplication with a division. So ln of 9 minus 8x is equal to 1. Great. And now I can do is change this into an exponential form, or use the inverse operation, which is the exponential function with the same base as the natural log. And what's that base? Of course, it's e, right? Or again, I'm just changing this into an exponential form. So e to the power of 1 is equal to 9 minus 8x. Now remember, e is a number, just like any other number. It's just, well, not like any other number. It's a special one. It's got its own name. But it's a number. You can take in your calculator. Again, it's 2.71 blah, 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 minus the 9 from it. So I'm going to put this in my calculator. E to the 1 minus 9. Clear the last thing we did. Where is e? Should be with ln. There you go. E to the power of 1, it always makes you do a power, is this, minus 9, is this value here, negative 6.2817. And then, of course, the last thing to do is to simply divide by this negative 8. X, yeah. So I'm going to take this and divide it by negative 8. And I'm going to get that x is 0.7852. Approximate answer, sure enough, because as soon as we turn that e into a decimal, it was an approximation. All right. Okay, so that's simple enough. Let's see what else could come our way. Now, there's all of a sudden a ton of logs. All right, no problem. So this is what we could do. We have learned in 4.5 that we can combine logs into one single log. And that's exactly what we're going to do. A log plus another log, as long as the bases are the same, which, by the way, again, these are common logs. You don't see a base written. That means it's 10 of x times 12. Remember, you get to combine the insides by multiplying them, is equal to a common log of 2x plus 10. Now, what can we do with this? Sure enough, drop the logs. The same thing as the exponential equations earlier, as long as the bases were the same. 2 to the something equals 2 to the something. Drop the 2's. How do we get to drop them? Simply because we're putting a base 10 under this log with base 10. Okay? But if you don't like the look of this, log of something equals to log of something, well, those two somethings must equal to each other. Okay? And there you go. It's a simple linear equation now. Get the x's to one side. Finish this up. So x is equal to 1. Done. Oops. I should take this off. Sorry about that. I need some more room here. There you go. All right. So we finished this equation. I got a few more for you, of course. Now, same thing. Let's practice on the rules. Log minus another log. What did the rule of logs say, or the properties of logs? When you minus two logs with the same base, what you get to do is divide their insides. Okay. And that's it. Next step, what are we going to do? Drop the two logs on both sides, right? They're log with the same base. Put a base of 10 under each one of them. So basically, their insides must also equal to each other. Now, what you see is a quotient, right? It's a rational equation now. Best thing to do would be to multiply by the LCD or cross multiply. In other words, move the x over here. Okay. And now it's a simple linear equation. Get the x's to one side. Divide by 73. So x is going to equal to 3 over 73. All done. Simple. I have another one just like it for you, and this is, I'm just going to want to solve it a little bit differently. So it's really just the same equation. Fine, the bases are now 8 and not 10, but it's the same thing. So maybe you didn't quite like the look of this fraction here. We have a way of fixing that. So what I can do is I can add this log of x over to this side, and then it's going to become a positive. Okay. And what if it becomes a positive? Well, the sum of two logs turns into one log of the product between. So I'm going to get 58 times x. And now, again, of course, with base 8, right? Keep the base. And now, because the bases are the same, what I can simply do, I don't need a parentheses no more, is make the insides equal to each other, which is the same thing we got here, right? But instead of getting a fraction and then cross multiplying, we moved this term over and became a sum, and then we got to right away multiply these, and now we don't have a fractional equation anymore, and that might look better for us. So in the end, we end up with the same exact type of equation. Remember, it was the same type of equation. So by moving this log over to make it positive, we had a product right away, which is much easier to now solve, because we didn't have to look at that quotient and possibly not know what to do with it. I know it could look weird. Okay, and there's your answer. All right, I got a few more for you. Same thing, except for these problems are just going to become a little bit more. So as you see, this time nicely, we have a sum between two logs, which is a nice thing, because that's simply going to turn into, again, what? The product between their insides. Okay, there you have it. So we get to multiply the insides of the logs, again, called the argument. And now we have a log equals to a log we can drop the logs again. What makes those logs drop? A simple base of 9 under each one of them. That's why I removed them, but you don't have to write that. So what I have here is simply a 2x squared minus 14x is equal to x squared minus 45. And now finally we have a little bit more to do. We have a quadratic equation. So definitely for quadratic equations, what do? Move everything to one side. So combining these like terms will get me a 1x squared minus 14x plus 45 is equal to 0. Factor it if you can. Numbers to multiply to 45 and add to 14 are surely 9 and 5. Okay. I'm going to write them here to the side. I have more room. So these are my two possible answers. X equals to 9 and x equals to 5. Now, we've been cruising along so far with these logarithmic equations. However, it's not as easy as just these mechanics. We have learned something about logs that we need to be careful about and we need to be mindful on. So what we've learned is that we can only have positive numbers inside the log. Remember earlier we put a negative inside the log and our calculator didn't want to give us an answer, right? It said domain error. So this looks all fine and dandy. Well, x is 9, x is 5, x is 6 over 57, whatever else we've been getting. As I said, cruising along. However, we never bothered checking our answers. And what I mean by checking our answers is even though you've done everything correctly, same as what happens when you solve square root equations and you need to check your answers for extraneous solutions, because even if you've done everything correctly, you still can get wrong answers. The same thing happens to the log. So what we simply need to do is take the answers we got, go back and make sure that they don't turn any of the arguments of your logs negative. So what do I mean by that? Is 2 times 9 a positive or negative? Definitely positive, so that's going to work. 9 minus 7, that's a 2, that's going to work. 9 squared minus 45, that's going to be fine. However, what happens if I plug in a 5? It's okay here, but right away, log of 5 minus 7, log of negative 2, that's not going to work. So as soon one of them fails, we have to exclude that. It can't be log of something plus undefined equals undefined. That's just not going to work, right? So you always need to go back and check your answers. Make sure none of the answers you got make any of the insides of your logs negative. So that's not a good answer, but this one's fine. So now let's just kind of go back. And again, this didn't happen. 3 over 73 plus 3 is positive. That's positive. 6 over 57 plus 6 is a positive value. So all you want to do is make sure that none of the insides of your logs turn negative. Look, we had a 1 answer here. Log of 1 exists. 2 times 1 plus 10, that's positive. So these were all fine. I did make sure 9 minus 8 times 0.7, blah, blah. That's going to still be a positive value. So again, I didn't stop you in your tracks. I already knew that my answers are going to be working out correct from the beginning. But now that this issue has come up, we need to remember to check. So here is one right away. I've given you a log equals to another log. Perfect. Just drop the logs. They have the same base. And there is our equation that we end up having to solve. X squared plus 13 is 7x plus 3. Okay, again, it's a quadratic equation, so I'm going to need to move everything to one side of the equal. So I'm going to get an x squared minus 7x plus 10 is equal to 0. All right, can we factor this? Sure. X minus 2, x minus 5. The two possible answers are 2 and 5. And again, both 2 and 5 are positive numbers, so you'd think it's all fine and dandy. However, let's see, are they going to keep the insides of our logs positives as well? 2 squared plus 13, Positive. 7 times 2 plus 3? Positive. Good answer. What about 5? Same thing. 5 squared plus 13 is positive. 7 times 5 plus 3 is positive. So both answers work. All right? But we checked and we know we did a fine job on this. All right, last one. Same thing. I have a log plus a log. You need to combine the logs, right? Again, you can't just drop all of these logs. It doesn't work that way. When can you drop the log? When you have one log equals to one log, one on each side, because again, you put a base of 9 under each one of them, and that's what makes them disappear. So, same thing here. Combine the logs first into one. So this is going to be a log with base 2 of multiply the arguments is equal to 3. Great. Now, I don't have a log on this side, so what am I going to do? I can change this logarithmic expression into an exponential form, or again, how do I make this one and only log disappear? I put a base of 2 underneath, yes? So 2 to the log with base 2 goes away, and I have x times x minus 2 is equal to 8. Or again, change into a logarithmic form. 2 to the third is equal to that. So again, as you see, we're getting here a quadratic equation. So I'm going to move everything to one side right away because we're going to have to factor it. So I'll get an x and an x, a negative 4, and a positive 2, right? So what are the two possible answers? X is 8, and x is negative 2. Okay, do you think both of these are appropriate answers? When you plug in the 4, yes, both are staying positive. When you plug in a negative 2, already this log here fails. So this is not a good answer. All right, so just 4 is. All right, so this is how logarithmic equations work. We've done quite plenty of them. You're going to practice some more. So I see that we have plenty of time on this video. Remember, I want to keep them under half an hour to just do a couple applications, a few applications. So many of these problems, same as in the beginning of chapter 4, deal with investments. So, there you go, better. Deal with investments. Okay, what does that mean? Money, right? Put money in the bank or whatever, have some sort of investment and let this money grow. Okay, so remember the two formulas we've used. The compound interest formula, that's if you have a finite amount of compounds per year, right? So n is the number of compounds per year. If it says semi-annually, that means twice, right? So it's a fixed amount. Monthly, that means n is 12. We are using, if you have an infinite amount of compounds per year, right? We call this a continuous compound. Of course, you can't put infinity in your calculator, so we're using the continuous compound formula. And most of these problems are going to deal with continuous compounds. Okay, so let's see what the questions are. It says, an initial amount of $6,000, okay, so that's our principal, grows at 5.5%. Okay, that's our interest rate. Compounded continuously. So what does this word continuously tell me immediately? It tells me that I have to use the continuous compound formula, right? So how much money will there be in the account after 4 years? So that simply means that I'm going to plug this numbers into my continuous compound formula. So P, which is 6,000, E, right, the Euler number that we use in this case, to the power of R, which is 5.5%. So again, don't forget to change this into a decimal number, times T, which is the time, so it says right here, 4 years. So plug all of this into your calculator. I'm not going to do that because I already have that value. So the answer is going to be, we're going to get $7,476.46. And anytime there's a word problem with units, you better write those units. So put a $sign to it. That's what I'm saying. Okay. How long will it take for the $6,000 to double in value? What does that mean? They double, and again, it's all compounded continuously, right? So it's still the PERT formula. So, in other words, what? We're starting with a $6,000. It says how long, so in other words, our answer is going to be asking for the time, yes? The interest rate is my 5.5%. So what does that mean that the money is going to double? That means at the end of this period of time, instead of $6,000, I'm going to have $12,000. All right? So this is the equation we need to solve. So we want to double the 6,000. Great, make it into 12,000. Okay. So how am I going to solve this equation for the time? I'm going to start right here. First things first, divide by 6,000. And that's going to get me a 2. E to the 0.055t. Now, how do I get into that exponent? How do I solve this exponential equation? We just practiced on this, right? Finally, we get to use that. So exponential equations, get rid of this base. So how do I get rid of this base of e? I'm going to undo it with its log. So log both sides, or again, change into a logarithmic form. That's the same thing. So what do I get? ln of 2. ln of e, that cancels out, is simply 0.055t. Okay, so now there's just one quick step to the time and divide by this decimal coefficient it's got. So the time, put this in your calculator, ln of 2 divided by 0.055 is going to get you 12.6-ish about. Okay, so 12.6 years, about. Of course, you don't need 4 decimal places, I just, whatever. So, the question is, how long will it take the $6,000 to grow by 50%? What does it mean that it grows by 50%? It means your $6,000 has grown by 50%. So basically, it's grown to a time and a half of what it was. 50%, I'm actually even going to write this, because it really doesn't matter what value you end up starting with, as we'll see in the next question. The amount of time will be the same. So by 50%, by half of what it was, right? So by means to add. 50% of 6,000 is just half of it, right? 3,000. So you add another 3,000, so 1, which is 6,000, and a half of it. So, of course, 9,000. The point is, as I said, the next step you're going to do is divide both sides by 6,000, and this guy's going to go away, and you will be left with just the 1.5. So as you see up here, what happened? We doubled this amount, fine, 12,000. Soon as I divided by this 6,000, what did I end up with? A 2, right? That's the double part. So it grows by 50%. You are left with a 1.5 of it, right? 100% means the same. It doesn't change. And by 50% means you're adding another 50% of it. So that's, whoops. There's the equal sign, Jesus. So 1.5 equals, I was going to say, where's my equation? Okay, so same thing. What am I going to do with this? Change into a logarithmic form. And then finally divide both sides by this 0.055. So if you put this in your calculator, ln of 1.5 divided by 0.055, you're going to get 7.0 0.37 many years. So you would have thought that maybe from your 100% to double it is 12.6 years, to just only grow half of that should have been maybe half of it, but it's not true, right? So it doesn't grow linearly, it grows exponentially. So that's why it's not just half the time, okay? If it was a linear growth, yes, it means it goes up at the same rate, up by this much, nicely linearly. Okay. So this is my question. What if we start with $1? How long will it take for that $1 to double? Okay. So if I start at $1 and make it grow continuously at 5.5%, what am I going to get? $2, right? Now, when you divide both sides by 1, what do you end up with? The same equation is up above. So this is what I was trying to show you. It really doesn't matter what amount you are starting with right here. Doubling it, well, twice as much. Growing by 50%, well, 1.5 as much of what you started. It doesn't, you don't even have to multiply because you'll be dividing it right back out. So the point is, whether it's $1 or $6,000 or any principal amount of money, P, as soon as you start solving it, the first thing you do is divide by that P out. So whatever it is you're starting with, it is really sad, but it turns out that it takes just as much time to double $1 as it does to double $6,000 or $6 million or whatever it is. It'll take 12.6 years to double your $1. So, lesson learned, you might as well start with a little bit more, right? That principle makes a huge difference. As you see, it takes the same amount of money, yes, to double $1 as it would $1 billion. Not that we have $1 billion to start with, but the more the better. Okay, let's try something else. Couple more problems and that's it. It says, some chemical compound decays at a rate of 2.5% compounded, there's your keyword, continuously. Continuously. Find the half-life of the compound. So let's see what that means. So first of all, continuously means we're going to use the PERT formula. I'm going to write that down right away, make it clear. Okay. What does it say? It decays at a rate of 2.5%, so 0.025. Okay, now it doesn't even say how much I'm starting with, which again, we just learned it doesn't really matter how much we're starting with. The point is, because, it decays at a rate of, so because it decays, be very careful. Decaying means that you have a negative rate, okay? Because a positive rate would make it go up. So the rate of growth is negative, okay? All right, so same as there's a doubling time, there is what we call a half-life. So a half-life is simply the time it takes for a decaying quantity to be cut in half, or to be left with just half. Okay, so the time it takes, so something that grows eventually will double up, right? So we call this doubling time. Something that decays eventually will be cut in half. We call this the half-life. Okay, I know it's kind of funny, not half time or so, but half-life. So what happens? This principal starting up amount that we are having eventually will just be half of it left. Does that make sense? So the problems that we did before, fine, I told you 6,000, we said we doubled it. So we ended up with just the 2 up front here. So as I said, it really doesn't matter what amount you're starting with. If you want to make it easy for you, fine, write 100. You start with 100, half of it ends up at 50. And you divide both sides by 100, guess what? You're going to have a 1/2 here. Okay, so to solve for t, what am I going to do? Log both sides, or change into a logarithmic form. And of course, the fact that this log is going to be negative, but you're dividing by another negative, so that makes the time back positive. So if you mess up on this, you know you messed up on the sign. So again, decaying means a negative rate of growth, right? So put this in your calculator, and you're going to end up with 27.7 years. And it's going to make it back. ln of 0.5 is a negative. 0.6913, something like that, I think. Okay. All right, last problem, and this is it. It says if $1,000 grows to $1,500 in 3 years, compounded continuously, find the interest rate. So again, continuously, there you go, there's my formula, right? Okay, so I have $1,000 I'm starting with. This one grows to $1,500, compounded continuously. We know this the time this time. All the problems before, we were given the rate, but we didn't know the time. And now fine, we know the time and we have to find the rate. So it's really the same exact question, because the rate and the time, they're both in this exponent as a product. You know one factor, you don't know the other, it really doesn't matter. So to get into here to this r, what's the first thing we do? Divide by 1,000. So there you have it, 1.5. What do? I want to eliminate the r, and how do I, the e? Take away that base of e. So again, put a natural log over this natural exponential function. And the last thing to do is divide by 3. So I'm going to go over here. So r is going to equal to ln of 1.5 divided by 3 is going to be a 0.135. Now, remember, this is a rate, it's an interest rate. So we like to write interest rate as percentage. So we're going to take this decimal number and change it into a percent number by multiplying back the 100th percent symbol. So 13.5% was the answer. All right, this is it. That's chapter 4.